Hello and welcome back to Calculus. As I've already mentioned to you a couple times, there will not be anywhere near as many videos this term as there were last term because of the live streaming and all that. But since tests are going to happen in person and since Wednesdays still have the remote component to them, there will be some videos on those days. So, we are starting a new unit today, Unit 8, Exponential and Logarithmic Functions. And before we get into this, by now you know how to find derivatives and integrals, both antiderivatives and definite integrals, of polynomials, of radical functions, of certain types of rational functions, of trig functions, well, most trig functions. But what we're going to do throughout this unit and the next unit is expand what you already know to deal with some other types of functions. In pre-calc and algebra 2, you learned about exponential functions, logarithmic functions. Well, we should be able to find the derivative, the rate of change, the slope of an exponential or a logarithmic function. Same with integrals. We should be able to figure out something that has an exponential function or a logarithmic function as its derivative, or we should be able to find the area under one of those things. So in this unit, we'll deal with exponential and logarithmic functions. In the next unit, we'll deal with some other types of functions. We're going to start looking at section 5.1 in the book, which is all about the natural logarithm. And you talked about this in algebra 2. You did a little bit more work in pre-calc. But I still think you probably felt a little unsettled by the natural logarithm. Okay, so it's a logarithm with a base of e. E is 2.7, 1828, 1828, 459045, and so on. But, like, why? Why does any of this matter? Why is this random number important? Where does any of this stuff come from? Well, the actual definition of a natural logarithm you couldn't really talk about last year, because it involves some ideas from calculus. But before we get into that, we need to recall something. We need to recall the integral of x to the n dx. Our power rule gives us x to the n plus 1 over n plus 1 plus a constant, and this works for every power except for 1. There's one power we cannot use this power rule on. What can n not equal? This isn't valid if n equals negative 1. If n is negative 1, okay, you can add 1 to the power, x to the negative 1 plus 1, x to the 0. Okay, that's okay. But then the denominator becomes divide by 0, and you can't do that. So what this really means is we can't do the integral of 1 over x dx, because that's like integrating x to the negative 1. I made you do things like this, integrating 1 over x squared, 1 over x cubed, but not 1 over x dx. Well, this is an issue. We should be able to figure out something that has 1 over x as its derivative, and more importantly, we should be able to find the area under that function. So to get around this problem, we do what mathematicians have always done. To get around the issue of square roots of negative numbers, they invented some other numbers called the imaginary numbers. To get around this issue, we're going to invent a new function. We're going to define a new function, and we're going to call it the natural logarithm. To get around this issue, we define a function that would get around this issue, and we're going to call it the natural log. Here's our definition. And this is a definition you did not get in algebra 2 or pre-calc. The natural logarithm is defined as, the natural log of x is defined as the integral from 1 to x of 1 over t dt, assuming that x is positive. copy this down, and then we need to kind of process what I just wrote. Okay, so you know what? I think the best way to understand this is by looking at a few examples. The natural log of 3 is defined as the integral from 1 to 3 of 1 over t dt. Okay, so you know what 1 over x, 1 over t looks like. It's that reciprocal function over there. The natural log of 3 is defined as the signed area, starting at 1, going to 3. The area underneath this curve, between 1 and 3, whatever that area is defined as the natural log of 3. Well, how can we get a decimal for this? You remember all those area approximations, right endpoint sum, left endpoint sum, midpoint sum trap. We could use those to get a decent approximation for the natural log of 3, but the actual value is the area under 1 over x from 1 to 3. Kind of a weird definition. Not at all how you saw this before. The natural log of 1, according to my formula, is defined as the integral from 1 to 1 of 1 over t dt. Oh my gosh, what's the natural log of 1? Well, you learned this last year that it would be 0, but why integrate from 1 to 1? There's no space there, you're going to get 0. So there is an important number related to the natural logarithm, and that number is e. You talked about this as the base of our logarithm, but we don't even care about that for right now. An important number is e, which is approximately approximately 2.718281828459045. Ask me in class why I know this. We'll talk Friday. But why this number is so important, this is the magic number, such that if you integrate from 1 to e of 1 over t dt, from 1 to e, this is that special number such that this area is exactly 1. Integrate from 1 to 2.718281828459045. That area will be exactly 1, which is like me saying the natural log of e is going to equal 1. Take a moment, make sure all this is in your notes, and then after that, we're going to take a look at the sheet in your packet of handouts titled Pre-Calc Review of Natural Logarithms. Okay, so before we move on and start doing some calculus with this stuff, I want to do a little bit of review of some things that you learned last year. The graph of y equals the natural log of x looks like this thing over here with a vertical asymptote at x equals 0, points at 1, 0, and e, 1, y, because the natural log of 1 is 0. The natural log of e, by the definition I just showed you, is 1. This is not the graph I was just showing you, the 1 over x. This is like what you get when you integrate that graph, the natural log of x. Vertical asymptote at x equals 0, domain, range, all that stuff. I want to graph two transformations of the natural log of x with you. As I'm pretty sure I mentioned at some point before, I find it really helpful to do transformations in different colors. So you might want to go get some different colored pencils, colored pens out. I'll wait, you can do that. In example number 1, I want to graph y equals the natural log of x minus 2 plus 4. I'm going to start by just graphing my parent function, y equals the natural log of x. That graph with a point at 1, 0, e, 1, a vertical asymptote on the y-axis, and something like this. And good enough. I have two transformations I need to apply. I need to deal with the minus 2, and I need to deal with the plus 4. What will the minus 2, which is inside my function, do to the graph? I hope that you said That minus 2 inside is going to move our graph right 2. So I'm going to take this point over here. I'm going to move it right 2 spaces. I'll take this point at 2.71828, move it right 2, so it's at 4.718281828. I'm also going to take the vertical asymptote, move that vertical line right 2 spaces. So my graph now looks like that. Then I need to deal with the plus 4. What's the plus 4 going to do to the graph? Plus 4 is going to move it up 4 spaces. Y equals the natural log of x minus 2 plus 4. We're going to go up 4. This point over here will go up 1, 2. No, it won't. I don't know why I said that. It'll go up 1, 2, 3, 4. This point's going to go up 1, 2, 3, 4. Take your vertical asymptote, move it up 4. Nothing's changing. Your graph is going to look like the light purple. When I do graphs, I usually color code my work on the side. If you do use different colors, I do need to see what each color represents. So I would just sort of show it the way I did over there. Number 2, take a moment, get the parent function sketched on that grid. E1, x equals 0. Parent function will look like this. First thing I've got to deal with is, the stuff inside that function, so that negative x. Do you remember what a negative inside the function will do to our graph? It's going to flip it, it's going to reflect it over the y-axis. This is a reflection over the y-axis. So I'm going to keep that vertical asymptote where it was. 1, 0 becomes negative 1, 0. E1 becomes negative E1. And looks like my red is running out. It shouldn't be. Then I'm going to deal with the 3. Do you remember what a number outside your function will do? Number outside your function is going to multiply the y values by that number. It's a vertical stretch by a factor of that thing. Multiply the y values by 3. This y value is 0, my new y value is 0. This y value is 1, my new y value is 3 times 1, or 3. Take that vertical asymptote, multiply it by 3, not going to change anything there. So my graph is going to look kind of like that. There will be a few graphing problems in the homework. Next thing we need to review from pre-calc, really algebra 2, some properties of logarithms, and you've been using these for a while. By the way, there's a whole lot more to natural logs than what we're reviewing right now. I'm just reviewing the specific topics we're going to need to be able to deal with calculus, and that's what we're going to do on all these pre-calc reviews throughout this unit and the next. Just the pre-calc pieces I need for us to be able to move forward. Our first property of logarithms, natural logarithms here, but really any sort of logarithm. Our first property says if you add 2 natural logs together, you can combine them into a single natural log, multiplying the things that were inside. If you subtract 2 natural logs, you can combine them to a single natural log, dividing the stuff inside, dividing a by b. If you have a number out front before your natural log, you can make that into a power inside your log. Natural log of a raised to the n. What we're going to mostly focus on is expanding logarithms. Using these properties, basically starting from something condensed, and I want to expand it into multiple logarithms, because we're going to see that will make some derivatives a whole lot more doable. And I'm going to ignore that for right now. So example number 1, I want to expand this natural log. Well, if you have a power, you're allowed to take that power and move it out front. So I can turn this into 2 times the natural log of 4x plus 1. Are you allowed to do anything else to this log? The answer is no. If there was a multiplication problem inside or a division problem inside, sure, I could go from there. But I have no property that tells me what to do if there's an addition problem inside your log. So this is as far as we're allowed to go in terms of expanding, which may not seem like a whole lot, but again, when we get to derivatives in a little bit, it's going to be a lot easier to deal with 2 times a natural log than a natural log of something squared. In example number 2, I see some things getting multiplied, I see some things getting divided. I can turn this into 3 logarithms. I can make this the natural log of x to the 6th plus the natural log of y cubed, because x to the 6th times y cubed gives me the thing up top, but since I'm dividing by z to the 5th, I'm going to say minus the natural log of z to the 5th. And honestly, we're going to add logs together to represent the things that were on the top of our fraction and subtract logs to represent the things in the bottom of our fraction. So if there were other things in the bottom, I would subtract natural logs for those as well. There's something else you can do with this. See if you can continue expanding this. Send your final expanded answer into Edpuzzle, please. What I was looking for you to do is to take your powers and move them out front. So I'm going to say 6 times the natural log of x plus 3 times the natural log of y minus 5 times the natural log of z. This is going to be fully expanded. Honestly, though, we're not going to deal with so many problems like example 2. The problems we're going to mostly deal with will be things that look like example 3. Okay. When we eventually go to find derivatives, this is going to be horrible. But if we can use our properties to simplify this, we can make it so much nicer. You know what? I have a feeling you can probably deal with this. See what you can do in terms of expanding. We'll talk in a moment. I see something up top, so I'm going to say the natural log of x squared plus 3 squared. Then I've got 2 pieces on the bottom. I'm going to subtract the natural log of x, and I'm going to subtract the natural log of, you know what, rather than saying the cube root, how about I say x squared plus 1 to the 1/3. I don't need to make it negative 1/3 because the reason it's in the denominator kind of gets taken care of by this minus sign over here. Now I'm going to move the powers out front. Your fully expanded version is 2 times the natural log of x squared plus 3 minus the natural log of x minus 1/3 times the natural log of x squared plus 1. That is our final fully expanded answer. There will be a few problems in the homework that cause you to just use this pre-calc review, expanding, condensing, things like that. Make sure this is all in your notes, and then we'll go back to the calculus. Okay, back to calculus. Let me see here. Derivatives. I want to do the derivative of the natural log of x. And actually, how about I go back to my definition of the natural log? The natural log is defined as the integral from 1 to x of 1 over t dt. How do we do the derivative of this? I think you should be thinking second fundamental theorem of calculus, the way we deal with derivatives of functions defined by integrals. I bet you can do this. What is the derivative of that function? By our second fundamental theorem of calculus, the derivative and the integral cancel. We'll just plug in this variable where the t was. We're going to get 1 over x. The derivative of the natural log of x is just 1 over x. Well, as long as x is positive. We can't do the natural log of a negative number, so we can't find the slope at a negative number if the function doesn't exist there. The derivative of the natural log of x is 1 over x. Let me show you some examples. First one. Let's say y equals the natural log of 3x. What rule are we going to have to use to deal with this? I hope you said chain rule because there's something inside my function. I'm also hoping this stuff's coming back to you because I know it's been a little while. To do the derivative of the natural log, the derivative of the natural log is 1 over the thing inside. So I'm going to say 1 over 3x. But by the chain rule, I now need to multiply by the derivative of the thing inside. I'm going to multiply this by 3. Oh, this is kind of interesting. My derivative is actually just 1 over x. Same as the derivative of the natural log of x. Let me try to show you another reason why the derivative is just 1 over x here. I suppose I could use my properties to expand this, and I could say y equals the natural log of 3 plus the natural log of x. What's the derivative of the natural log of 3? Well, this is just a constant, so the derivative of a constant is 0. What's the derivative of the natural log of x? 1 over x. Yeah, my derivative, just 1 over x. How about you try this one? Please find the derivative of y equals the natural log of x squared plus 1. And I think I'll have you send this into Edpuzzle. Just be a little careful writing parentheses in there so it's clear what you mean. This is going to be another chain rule problem. 1 over the thing inside, so 1 over x squared plus 1, times 2x. Your answer is going to be 2x over x squared plus 1. That's your derivative. Remember, derivatives are finding slopes. This formula would give us the slope everywhere. By the way I'm going to kind of organize this unit, we're going to first start by just kind of taking care of all the math stuff. How do we do derivatives? How do we do integrals of logs, exponential functions, all that? Then we're going to spend 2 days on all the applications of this stuff. How can we do some tangent lines, area under a curve problems, initial value problems, curve sketching problems, where we can apply all this stuff? We will definitely get into those, but I'm going to save those for later. Next problem, y equals x times the natural log of x. What rule do I have to use here? Oh, I really hope you said product rule. Go use the product rule. Whoops. Go use the product rule. I will deal with that later. I should probably turn off the sound on my phone. Okay, so I'm going to use the product rule. Wait a minute, you're going to go use product rule. Go find the derivative. I'm just confused. Okay, I'm back, sorry. First times derivative of the second, x times 1 over x, plus second times the derivative of the first, natural log of x times 1. I'm going to put things together here. I'm going to get 1 plus the natural log of x, and that's my derivative. One more, and then we'll make them a little tougher. Let's look at y equals the natural log of x cubed. I'm going to need to use the chain rule here, but what's my outside function, the cube or the natural log? I hope you said the cube. The cube is my outermost function. You're going to have to take care of the cube first and then deal with what's left. See if you can do this. I'm going to get 3 times the natural log of x squared. Then I'm going to multiply this by the derivative of the natural log times 1 over x. And I think I'm just going to leave it. By the way, this is the natural log of x, the whole thing getting cubed, very different than saying the natural log of x cubed. That's implying just the x is getting cubed, and that's inside your natural log. Not the case here. Okay, a few harder problems. Y equals the natural log of the square root of x plus 1. I could totally do this by using the chain rule and all that stuff, but if I first simplify this problem by using my properties, the work is going to be a whole lot easier. So let's say simplify first using the properties. I'm going to get y equals the natural log of x plus 1 to the 1/2, and you can move your 1/2 out front. Y equals 1/2 times the natural log of x plus 1. That's going to be a lot easier to find the derivative. Go find your derivative. Derivative of the natural log of x plus 1, I do need chain rule. So 1 over x plus 1 times the derivative of x plus 1, that's just times 1. I'm okay with an answer like this. Would be even better if you said 1 over 2 times in parentheses x plus 1. Don't say 1 over 2x plus 1. That would be wrong. I guess you could say 1 over 2x plus 2. That would be okay. But that's your final answer. And because I used the properties, my work wasn't quite as intense as if I just started using chain rule and all that messy stuff. Let's try this one. Y equals the natural log of x plus 4 over x minus 2. Rewrite that using your properties, please. This is going to become y equals, note I'm saying y equals, not y prime. I haven't done the derivative yet. I'm just rewriting. The natural log of x plus 4 minus the natural log of x minus 2. If I left it like this, I'd have to use chain rule. And inside the chain rule, I'd have to use quotient rule, and it would be unpleasant. This, not a big deal. Go find your derivative. Y prime is going to equal 1 over x plus 4 times 1 minus, derivative here, 1 over x minus 2 times 1. I guess you could put them together, get a common denominator. I'm not going to bother, but I'm going to assume you can handle that. Wait a minute. No, never mind. I think that's good for a final answer. Okay. One more with the properties. Another piece of paper. Okay, let's see. Where are we? I want you to find the derivative of this mess. Y equals the natural log of x times x squared plus 1 squared over cube root of 2x cubed minus 1. I want to see if you can do this. Don't you dare try it this way, the way it's written. Use your properties first to write it as 3 fully expanded logs. Then do your derivative. There will be some chain rule involved. That's okay. But see if you can do this. I think you can. So I'm going to get that. I'm going to go and move my powers out front. So natural log of x plus 2 times the natural log of x squared plus 1 minus a third times the natural log of 2x cubed minus 1. Notice this isn't y prime, this is just y. I'm just rewriting. Time for the derivative. Derivative of the natural log of x, 1 over x, plus 2 times. I need chain rule. 1 over x squared plus 1 times 2x. I'll clean it up in a moment. Minus 1/3 times. Chain rule again. 1 over 2x cubed minus 1 times 6x squared. I should simplify a little bit. So y prime equals 1 over x plus, looks like 4x over x squared plus 1. Over here, 6x squared over 3 times, I can simplify that, 2x cubed minus 1. I'm going to get 1 over x plus 4x over x squared plus 1 minus 2x squared over 2x cubed minus 1. And no, I would not want you to put that together in a single fraction. I'll give you a moment to make sure that's all in your notes, and then we've got a few more things to look at. There's another derivative rule I just need to show you quickly. The derivative of the natural log of the absolute value of x equals. Well, okay, so if we do the absolute value around x, I could plug negative numbers into this thing, and that would work. What is this function really? This function is really, let's see, just the natural log of regular x if x is some positive number, and it's the natural log of negative x if x is some negative number. If I try to find the derivative of this thing, f prime of x is going to equal, hello, f prime of x is going to equal derivative of the natural log of x, 1 over x, when x is greater than 0, 1 over negative x times negative 1 if x is less than 0. This is really just 1 over x. Which actually means if you want to find the derivative of this thing, it's still just 1 over x. And this one's valid anywhere that x doesn't equal 0, as opposed to the derivative of just the natural log of regular x, which is valid when x is greater than 0. So here is our new derivative rule. Basically, what this is saying is we've got f prime. I hope it's still on the screen. I am on the screen. Thank you very much.
You're very welcome.
Thank you. Let me think. If our original function is just the natural log of x, its derivative would just be something like that. But if I do the natural log of the absolute value of x, then I have also the reflection over the y-axis, which means the derivative is this entire thing over here. Don't worry too much about where this is coming from. Just realize if there's absolute values inside your derivative, it doesn't change anything. Your derivative is still 1 over x. Therefore, y equals the natural log of the absolute value of the cosecant of x. If I want to find the derivative of this, the absolute value bars do not matter. The derivative of the natural log of something is 1 over that thing, not the absolute value, just 1 over the cosecant of x, times the derivative. What's the derivative, by the way, of the cosecant of x? We should still know that. Maybe you said negative cosecant x cotangent x. Might be time to dig those back up again and do some refreshers on that. We're going to get, well, this is kind of nice actually, those cancel. We're just going to get the negative cotangent of x. Ooh, wait a minute. So if I actually went backwards, if I gave you this derivative and wanted to know what it came from, this is going to be related to our integrals of trig functions. We'll deal with that in the next section, but we're getting close to being able to deal with integrals of trig functions we couldn't have dealt with before. Let's try another one. Y equals the natural log of the absolute value of the sine x plus 1 over the cosine of x. This isn't 100% formally correct, but it will work for our purposes. I can use my properties to say this is the natural log of the absolute value of the sine of x plus 1 minus the natural log of the absolute value of the cosine of x. It'll work out in the end. Go do your derivative. Y prime is going to equal 1 over sine x plus 1 times the cosine of x minus 1 over the cosine of x times negative sine x. Okay, so y prime is going to equal cosine x over sine x plus 1. Deal with that over there, plus sine x over cos. Oh, you know what? I could probably say that in a better way. We can say this is cosine x over sine x plus 1 plus the tangent of x. As far as you're concerned, as far as derivatives go, the absolute value bars don't matter inside your natural log. Make sure this is all in your notes. And then I have one last thing I want to go through with you. A couple weeks ago for that Delta Math assignment, I made you review some implicit derivatives. Well, they're coming back here. Implicit differentiation. Don't be too excited. First example. I want to find the derivative dy dx for x plus y plus the natural log of x equals 2y cubed. You know what might be fun to start this? Might be fun to go to Desmos and see what this looks like. How about you go do that for a moment? I'll make the video pause. Go graph the implicit function x plus y plus the natural log of x equals 2y cubed. So I hope you saw what that graph looked like. Clearly there are slopes in different places. I want a formula that will find the slope. Well, the way implicit differentiation works, remember, is we're going to go find the derivative of the left side, and we're going to go find the derivative of the right side. The derivative of x, just 1. But what do we say the derivative of y is? Derivative of y is dy dx. Derivative of the natural log of x is what? Oh, I hope you know this one. This is what we spent the whole video on. 1 over x. On the other side, see if you remember how to do this. What's the derivative of 2y cubed? I need chain rule here. This is 6y squared times the derivative of y, so times dy dx. I'm going to move my dy dx's to the other side, so 1, no, I'm just confusing myself, 1 plus 1 over x equals 6y squared dy dx minus dy dx. I'll factor out a dy dx. To get that thing. And then I'll divide. And I'm going to get dy dx equals, divide both sides by this, I'm going to get 1 plus 1 over x all over 6y squared minus 1. You think I'm okay with that answer, though? Of course I'm not. You're not okay with you leaving fractions inside fractions. The way we can finish this is we can multiply the numerator and denominator by x. When I do that, I'm going to go and distribute up top. X times 1 is x. 1 over x times x is 1. And the denominator, I'm not going to bother. I'm just going to leave it factored out. And I'm going to say that this is my derivative. I'll pause so you can make sure this is all in the notes. We have one more. I want to find dy dx for x to the fourth plus the natural log of x squared y minus y to the third equals 2. Oh, go to Desmos for a moment. Graph that thing. Let's see what it looks like. This is going to be a little bit painful if I try to deal with this as is, because I'd have to use chain rule, but product rule, and it's going to be a mess. Any ideas how I can make this problem easier? I hope you didn't respond, just don't do it. No, we're going to do this problem. We can make this easier by using our properties of logs. I can rewrite that thing in the middle as the natural log. I've got a product, so I can say natural log of x squared plus the natural log of y. Minus y cubed equals 2. Well, why stop there? We can go further. We can say this is x to the fourth plus 2 times the natural log of x plus the natural log of y minus y cubed equals 2. Now, it's still going to be a little messy, but I feel like it's in a much better form for us to find the derivative. I'm going to go find the derivative of both sides. Actually, no, I'm not. you're going to go do the derivative of both sides, and then together we'll clean it up. Go do your derivative, please. Okay, 4x cubed plus 2 times 1 over x, I'll just say 2 over x, plus 1 over y, dy dx, minus 3y squared, dy dx, equals 0. Let's finish it together. I'm going to move the terms with the dy dx's to the right side. So I've got 4x cubed plus 2 over x equals 3y squared dy dx minus 1 over y dy dx. I'm going to get 4x cubed plus 2 over x equals dy dx times 3y squared minus 1 over y. Divide 4x cubed plus 2 over x over 3y squared minus 1 over y. What are we going to have to multiply by to get rid of our fractions inside fractions? I'm going to multiply this thing by xy over xy. The x I'm actually going to distribute up top, but the y I'm going to leave factored out. I'm going to get y times 4x to the fourth plus 2. In the bottom, I'm going to leave the x factored out, but I'm going to distribute the y. I'm going to get x times 3y to the third minus 1. That is my answer. That is my derivative. That is the formula that would find the slope at any point on that implicit curve. And I think that's about all I have to say for this video.